July 1st, 2025. Astronomers scanning the skies spot the third ever interstellar object crossing into our solar system. Except this one is not just unusual, it is rewriting the rules. 3I Atlas erupts, dumping millions of kilograms of material in a frenzy that should not be physically possible, with numbers that break everything we know about cometary science. If our best telescopes say the nucleus is tiny, how could it unleash such an explosion? The answer starts with the moment it was found. The Atlas survey team in Rio Hurtado, Chile, spent the night of July 1st, 2025, sifting through a flood of automated alerts. Most nights, the system flags stray asteroids or the endless parade of routine comets. But this time, the software hesitated. The object in question was not following the usual script. Its orbit was unmistakably hyperbolic, with an eccentricity greater than 1.1, far too fast and steep to be bound by the sun's gravity. Within hours, telescopes from Hawaii to South Africa were racing to capture new data. Pre-discovery images from mid-June, dug up by the Zwicky Transient Facility, confirmed what the initial math suggested. This was no local wanderer. The Minor Planet Center made it official on July 4th, 2025, assigning the name 3I Atlas, only the third interstellar object ever confirmed. The mood in the control room shifted from skepticism to celebration. Internal emails recall a burst of applause as the third I was logged. For a moment, the team was at the center of a historic event. The last time the solar system received an interstellar guest, it was Oumuamua, a silent, rocky enigma that slipped past in 2017, betraying no cometary activity. 2 years later, 2I Borisov arrived in 2019, a textbook comet that behaved exactly as predicted, shedding gas and dust in a familiar arc. But 3I Atlas immediately defied easy classification. Early images from TESS and Hubble revealed a cometary coma, but the object's activity started much farther from the sun than any typical comet. Its faint glow, barely reaching magnitude 12 at its brightest, belied the extraordinary forces at play. Scientists recognized instantly that this visitor was neither inert like Oumuamua nor predictable like Borisov. It was something entirely new, straddling a line that no cataloged object had ever crossed. Astronomers began crunching the numbers as soon as 3I Atlas was confirmed. The first surprise arrived in August, when measurements showed the comet was losing about 330 kilograms of material every second. By late October, that figure had skyrocketed to nearly 2,000 kilograms per second, an order of magnitude higher than any typical comet of similar size. The math didn't stop there. To sustain even the lower end of these mass loss rates through normal solar heating, the object would need an active surface area of at least 1.6 square kilometers, or about 617 square miles. That's the area of a sphere over 14 kilometers across. But Hubble's sharpest images left no doubt. The nucleus of 3I Atlas measured no more than 1 or 2 kilometers wide. There was nowhere for that much ice and rock to hide. No cloak of dust, no trick of perspective could explain away the missing mass. The energy pouring from the sun simply wasn't enough to drive such furious outgassing from such a small core. Every calculation pointed to the same conclusion. The observed activity broke the rules of cometary physics. The numbers didn't just strain the models, they snapped them. For weeks, research teams ran and reran their simulations, searching for a loophole. None appeared. The paradox was now undeniable. Something was happening to 3I Atlas that standard comet science could not explain. The leading explanation among comet researchers came down to numbers. When a comet breaks apart, each fragment exposes a fresh surface to sunlight. If the nucleus of 3I Atlas shattered into thousands or even millions of pieces, the total surface area would skyrocket. More area means more ice vaporizing at once, turning a small, quiet nucleus into a sprawling, hyperactive debris field. This scenario, called catastrophic fragmentation, could multiply the sunlit surface well beyond what a single, intact object could provide. The result would be a massive dusty cloud, with each fragment contributing to the outpouring of gas and dust. Observers would expect the comet's brightness to surge as sunlight scattered off countless grains, mimicking the effect of a much larger object. The math checks out. To sustain the observed mass loss, the total area needs to be hundreds of times greater than the original nucleus. This natural explanation, dramatic as it sounds, became the working hypothesis for the world's observatories. Spectroscopic data from August and September delivered an unexpected twist. As 3I Atlas brightened, its light shifted toward the blue end of the spectrum, a trait almost never seen in fragmenting comets. Standard comet breakups fill space with dust and rocky grains, scattering sunlight and giving the coma a yellowish or reddish glow. But here, the blue surge pointed to something else entirely: the dominance of ionized gases, especially carbon monoxide. Instead of a dusty haze, the spectra showed sharp emission lines from excited molecules, with very little evidence of the broad, featureless scattering that dust would produce. For comet researchers, this was deeply unsettling. The blue color implied that sunlight was interacting with jets of gas, not clouds of solid debris. One scientist compared it to a snowball tossed into a furnace that somehow glows with a metallic blue shine, instead of vaporizing into steam and dust. The expected signatures of a typical cometary explosion, broad dust tails, reddening and fading, were missing. This spectral fingerprint did not just challenge the fragmentation scenario, it forced astronomers to question whether any known natural process could explain what they were seeing. November 9, 2025, brought a revelation that no one in the professional astronomy world had anticipated. Michael Buchner and Frank Niebling, two dedicated amateur astronomers working overnight from the UK, managed to capture a set of images that would send shockwaves through the comet research community. Their session was nearly canceled by weather and software glitches, but after hours of troubleshooting and a borrowed observatory mount, their efforts paid off. The images did not show a chaotic, expanding cloud of debris as expected from a shattered comet. Instead, they revealed something far stranger: sharply defined, geometric jets radiating from the core of 3E Atlas. At least 7 distinct jets appeared, each maintaining a remarkable coherence as they extended outward. One structure, an anti-tail, stretched nearly 1 million kilometers toward the sun, directly against the direction the solar wind should push any cometary material. On the opposite side, a luminous plume reached almost 3 million kilometers into space, dwarfing the scale of any known comet tail. The organization and persistence of these features defied every prediction for a natural, thermally driven explosion. Standard fragmentation should have produced a diffuse, randomized spray, not a set of collimated outflows with such regularity. These images forced astronomers to confront a new reality. Whatever was happening inside 3I Atlas, it was not following the script of any comet ever observed. Avi Loeb's proposal landed like a thunderclap in the middle of a scientific storm. If the organized jets and sudden bursts of energy could not be explained by ice and sunlight alone, then perhaps something else, something engineered, was at work. Chemical thrusters, he argued, could hurl material away at speeds 10 times faster than natural comet outgassing. That would mean far less mass was needed to create the measured acceleration. In this scenario, the jets would not be random, but deliberate, their geometry a clue to intentional propulsion. Not everyone was convinced. As Loeb's paper made headlines, teams around the world rushed to collect every possible piece of evidence. Sensitive radio campaigns, including those at Meerkat in South Africa, trained their receivers on 3I Atlas, searching for the faint signature of hydroxyl, a byproduct of water breaking apart in sunlight. Such a detection would be a smoking gun for natural cometary activity, tipping the scales back toward ice and rock. Time was running out. The object would make its closest approach to Earth on December 19, 2025. After January, it would fade beyond the reach of even the most powerful telescopes. The world's best observatories scrambled to schedule emergency observation time, knowing this was the last, fleeting chance to catch the interstellar visitor in high resolution. The outcome, natural or engineered, remained suspended in the balance, with only weeks left to decide. Right now, telescopes capture a phenomenon no theory neatly explains. Each fragment and jet from 3I Atlas challenges what we know about the universe. As we watch, the boundaries of natural law and our assumptions are tested. Sometimes the cosmos answers with a question instead of an explanation.